Okay, so in this section, our first speaker is Iki or Jansky Ma from Max Planck Institute. You will talk. Yes. You'll talk about a radio polarization study of an extragalactic source with high rotation measurement.
Thank you. Can everyone hear me? Okay, so today I'll talk about my project on the study of radio polarization study of extragalactic sources with high rotation measure. So first I will give a very brief reminder to you about how we probe the magnetic field by measuring the synchrotron radiation. And then I will move on to talk about my project. So as Anna's talk also revealed on Monday, we can probe the magnetic field by observing the polarization of synchrotron radiation. So if let's say this the emitting medium here with the magnetic field along this direction, then the polarization plane will be along the orthogonal direction. So all we need to do is to measure the polarization and add 90 degrees to it, and all we get is the magnetic field configuration in the system. And this, as the polarized light transfers through the magnetized plasma medium in the thinning screen, this polarization plane will also rotate because of Faraday rotation, with the amounts of rotation given by the formula here. So this rotation measure RM here carries the information of the magnetic field in the intervening system. So we can get both the magnetic field in the plane of sky and also along the line of sight from polarization measurements. And in order to get this RM, all we need to do is to observe at 2 or even more different frequencies. Like as shown here, let's say we observe at 3 and 6 centimeters, then we can just draw a line through these 2 data points, and the slope will be the rotation measure to the line of sight or to the source. And if we extrapolate this to a lambda of 0, we can get the intrinsic polarization angle. But then by measuring the RM and intrinsic angle this way often comes with ambiguity, because let's say if we measure at just 2 frequencies, there are infinitely many ways to draw through these 2 data points, because the angle wraps around. So let's say we can draw a line here which gives a slightly lower rotation measure, or we can draw it this way, which gives a much higher rotation measure. So one way to tackle this is to, well, in the modern standard, we can carry out broadband observations, like as shown here. If we have like hundreds or thousands of data points, then the RM we get we can remove the ambiguity this way. So it's very important for us, if we want to be very sure about the RM, we can have broadband observations to confirm the rotation measure. But all we have discussed so far is just on simple systems that the polarization angle strictly follows the lambda square law. But then in more realistic and complex situations, the polarization angle will deviate from the lambda square law, as shown in this simple example here. So let's say, so I'll first introduce a term called the Faraday depth. So if we say that a source is at a Faraday depth of phi, it just means that the polarization will go through a Faraday rotation of 5 times lambda square. So let's say we are observing through a line of sight, looking at a radial lobe at a Faraday depth of 10 radians per meter square. And in front of this, we also have a galactic foreground between -2 and 2 radians per meter square. In such a relatively simple system, the polarization will go crazy, like as shown in this figure here. This solid line is what you will expect to see if you observe this system. So it's quite difficult to get define RM in this more complicated case. So what we can do is to use a technique called the RM synthesis, which is just a Fourier transform of the complex polarization at different frequencies. And what we will get is called the Faraday depth spectrum. So this Faraday spectrum is the polarized intensity as a function of Faraday depth. So let's say for this system, after using this RM synthesis technique, we will get this Faraday spectrum. So we can recover the Faraday foreground here, and also the radial lobes here. So even for complex cases, it's powerful because we can decompose into different systems along the same line of sight. But even for simple cases, we can still use this technique to get the RM value by just locating the peak in the RM spectrum. So now I will start talking about my project. So my project is based on the NVSS RM Catalogue. So as shown in Karl's talk, it's very important information if you want to study the magnetic field in the foreground. So they have got almost 3,800 sources, and to get the RM for the sources, all they did was to use the 2 NVSS bands to get the RM. So as I've shown in a few slides before, this method is tricky to tackle the nπ-ambiguity this way because, well, we are just limited by the data that they have. And to tackle this ambiguity, they used the bandwidth depolarisation. So what they did was because they have the measurements at 2 different bands, so they can try to constrain the bandwidth depolarisation observed by the NVSS. And then they compared with what would be expected at different RM values. So by comparing these 2 values, they can try to get the most likely RM value, which is a very brilliant idea, but still, the measurement is limited by the NVSS observation. So we want to test how good this method is to tackle this nπ-ambiguity. But then it's tricky to start this project, right? Because there are thousands, tens of thousands of sources. So we tried to look away from the galactic plane. And if we look away from the galactic plane, we found that most of the sources have a rotation measure of less than 150 radians per meter squared. But then a few of them have rather extreme RM values of over 300 or so. So these sources are the prime candidates of wrong RM measurements in their catalog because, well, it's kind of unexpected to see such a high RM away from the galactic plane. So maybe they have done something wrong to tackle to get the real RM value. Or maybe these are indeed some exotic sources with a very high rotation measure, which we also want to look into. So this is a brief overview of the 2 kinds of sources that we are expected to see from by observing these sources. So for the first category, we call this the imposters because the NVSS gave us the wrong RM value. This will be very interesting if we want to study the foreground magnetic field because if the RM value is wrong in the catalog, then it will affect the conclusions in subsequent studies. And to locate these sources, we can use broadband polarization observations, which will give us RM values free of ambiguity. And the other category is that maybe the NVSS RMs are right, and we call this the outliers. So these outliers could be a very interesting source to study, which by using broadband observations and RM synthesis will also give us some insights. So you can see that that's why we carried out broadband polarization observations to study these sources. We used the JVLA to observe these 23 sources with a very high rotation measure from the NVSS. And we observed at the L band in the array configuration. And this is a table showing the results that we have so far. So we have analyzed about 15 sources so far. And we have separated the sources into these two classes. And we also identified a new class of sources, which I will go through a bit later. And the first thing we can see is that the NVSS RM and our RM value do not really agree with each other. So there's about 10% or so difference in RM. So this is interesting because maybe these high RM sources could indeed have a fluctuation in rotation measure, which is not well studied so far. And we have also located for the imposters, we have located that about 25% or so of them have wrong RM value. So the next question would be, so there are about 40,000 sources in the NVSS RM Catalogue. So we want to see if, tell if some of the low NVSS RM sources could actually have high RM, could actually have a high rotation measure, which will, well, it could increase our sample size. And if we can locate these sources, it could affect, we can tell if the subsequent studies based on this RM catalog could deviate. And then, yes, here is a plot showing the NVSS RM versus the JVLA RM. So JVLA RM is our measurements. So this data points line on this line means the values more or less agree with each other, but you can see that it deviates quite significantly from what we expected. And here is the imposters and also the extreme variables. So now I will go through the two of the more interesting sources in the sample. So the first one we are going through is what we call the extreme variable. So first, when we went through the data and we found that the RM we get is significantly different from the NVSS RM. So we tried to use our data to go through the NVSS RM's analysis to try to get the RM value by their method. So we will expect that we will retrieve their RM value, but it turns out that we failed to reproduce their RM value, but instead we got back our value. So it's interesting because this might mean that this source could be varying, because maybe their measurements 20 years ago with our measurements, the source could have changed in terms of polarization properties and flux densities. We have looked through the literature and found that it indeed is the case. And this source also have a very flat spectral index, so we are thinking that this source could be varying in both rotation measure and flux density. And if this is the case, if the NVSS RM value was indeed correct at the epoch, this could be one of the most extreme change in RM that we have observed so far. And for this source, because I'm kind of running out of time, I'll very quickly go through this. So the second source I highlight is an imposter. So we found that, so this is the position angle against the lambda square for this source. And these two bands are the NVSS bands here. And you can see it deviates from the lambda square law significantly in these two bands. So this could be why their study gave a wrong RM value. It's because the source is fairly complex, and that's why by studying the bandwidth depolarization, they get the wrong RM value. And so this is my conclusion slide, and also highlighting some of my plans for future studies. Thank you.
Just one question. Okay, then that's exactly okay.